Well, welcome. Welcome, everyone. Well, our speaker today is Pablo Moreno. Most of you know him. He did his PhD in physics in the Universidad Complutense de Madrid, and after that, he was a master student here at the FISC. And he is now in the third year of his PhD, more or less, roughly.
Yeah,
more or less. So he is now going to tell us. Well, he is working in the context of the SUMA-ECO project on seagrasses and dynamics of Posidonian mediums and so on, but he is also doing more theoretical research on dynamical systems and application theory. And that part is what he is going to explain us. And the title is Type 1 Excitable Medium, Theoretical Framework for Space-Extended Excitable Systems. So Pablo, go ahead.
Okay, thank you. Hello, as Damian told, I'm Pablo Moreno. I'm a PhD student here in the FISC under the supervision of Damian Gomila. And today I'm going to present some of the work I've been doing during the last years. So the name of the talk is Type 1 Excitable Media, a theoretical framework for space-extended excitable systems. And I'm going to present some work I've been done with some colleagues here in the FISC. That they are Andreu Ariño y Prats, Daniel Ruiz Reynés, Manuel Matias, and of course my supervisor, Damian Gomila. So first of all, I'm going to present a little bit the contents I will give in this talk. First, I'm going to give a little bit of motivation. Why are we doing this? Secondly, I will make an introduction explaining excitability. That is the topic of this talk. I'm going to... Okay. Okay, everything's okay. I'm going to start with local excitability. That's just considering temporal systems. After that, I'm going to explain a little bit about excitable media, that is systems that also have a space. I'm going to present our model, the results we have, and finally, I will give some conclusions. So first of all, let's go with the motivation. All this project born when studying Posidonia oceanica. Posidonia oceanica, for the ones here that do not know, is a marine plant that is attached to the ground of the sea and have clonal reproduction. Usually these plants create very extensive meadows, but under some circumstances, for some range of mortality, they create more exotic patterns. For example, here we have in this image that was taken in Pollensa, here in Mallorca, how the Posidonia have arranged in a different distribution. No? It's creating these kind of rings that expands in time, and these rings interact with each other when they collapse. For example, here we can see this ring that have collapsed with another one and they break. Usually this kind of behavior is associated with excitability. But when looking for the mechanisms that are behind this kind of behavior in the Posidonia oceanica, we saw that it was not compatible with the classic explanation that is given for excitability, that it's something else happening there. So, well, we started our research and find that there was another kind of excitable media that wasn't considered too much before now, and it's the type 1 excitability. No? Before, everything was considered usually as a type 2 excitability in extended media. So now that I'm motivated a little bit, I'm going to get one step back. I'm going for just temporal systems. Temporal excitability is a property of some dynamical system, and they are usually defined with a system of ordinary differential equations, this one, where the temporal derivative of the different variables is given by a function of that variables, but also of some parameters. So in an excitable system, we usually have a fixed point in the system. Here I'm plotting one of the variables as a function of time. And this fixed point is a point of the system that do not change when times do not change in time. Here, there is this stable fixed point given by this black line there. And if we make a small perturbation of it, for example, this blue dot there, as it is stable, it will decay and it will converge into this stable fixed point that we call the rest state. Nevertheless, if we put a perturbation large enough, for example, this red dot here, it will make a long trip around the phase space, and finally going back to the rest state. Here is the excitable behavior, and well, this trajectory is what we call an excitable trajectory. Usually, this kind of behavior happens close to the destruction of some large amplitude oscillation, like these ones. These oscillations usually break through a bifurcation when changing one parameter, for example, mu. So tuning this parameter, we can change from the oscillatory regime to the excitable regime. And this happens through one bifurcation where this oscillation is destroyed. As you can see here, the excitable trajectory still follows some similar trajectory as what the oscillatory oscillation did. No? For example, well, here you can see it easily, that the oscillations and the trajectory are quite similar. No? Depending how this oscillation is break, how it's destroyed, we can talk about two different kinds of temporal excitability. In fact, if the frequency of the oscillations goes to 0 when we do the change to the excitable regime, we would talk about type 1 excitability. And this usually happens through an on-off clinic or a snake bifurcation. I will explain it better some slide above. But well, this is the idea, that the frequency goes to 0 before the change to the excitable regime. On the other hand, the type 1 excitability, the frequency of the oscillations do not go to 0 in the point where they are destroyed. But well, yeah, they have a finite frequency at that point. And this usually happens in a hop with a canard. And a hop with a canard is a bifurcation with where this small amplitude of oscillations appears, but this oscillation become very big in a very short parameter range. So we can understand it as a destroy of this amplitude, very big amplitude oscillation. This usually happens in a slow, fast system that have two different time scales. The most paradigmatic case of this kind of system is the Fitz-Hugh-Nagumo model that I'm going to explain a little bit now in the excitable regime to understand a little bit what is type 2 excitability. So Fitz-Hugh-Nagumo, as I told, is a model. Here we have two different variables that change in time. And there is two different time scales that are given by this parameter eta here. So eta is a very small number. And this makes that one of the variables, here the u, has very fast dynamics, while the other has very slow dynamics. So yeah, usually the chains are going to be resolved in the fast dynamic, in the fast variable, and after that go slower in the other one. Usually f and g, that are the two functions that define the dynamics, are in for the fast variable cubic term, a cubic function, and it's a linear function for the slow variable. In the excitable regime, we can draw the phase space of this system, and we have something like this, where this red line here, this red curve, is the points in the phase space where the fast variable do not move, because this function f is 0. On the other hand, we have this other line here in blue that is the point in the space where the slow variable do not change, because this function here g is 0. No, we expect now that under the red curve, the function f will be positive, and so we have this very fast dynamics going to the right, while over the red curve, we have the very fast dynamics going to the left. Similarly, with the slow dynamic variable, we have on the left of the blue curve that is go down, and on the right that is go up. And the point where these two lines, these two curves meet, is a point where nothing changed. So we have a fixed point. This fixed point is stable. Is the rest state I told before about in excitable system. So if we make a small perturbation, well, large enough perturbation of this point to go to the excitable trajectory, like this one, what we have when crossing this minimum there is that we will have this very fast dynamics to the right, this, then the slow variable is the one that rules the movement of the system, and it will go slowly to the top, go now to the left, very fast, and then again slowly down. So what happened here is the excitable trajectory. No? So we have typically in this kind of systems a square shaped trajectory like this one, where you can see the fast parts are this one here, and the slow is this slower regions in the middle. So in this kind of system of type 2 excitability, we have usually slow fast systems. The bifurcation to arrive here is usually a half bifurcation with a canard. They have a very well-defined frequency. The excitable trajectory have a very well-defined time, because most part of the dynamics occur during the slow dynamics part here. So the duration of all the pulse is not very initial condition dependent. And finally, something that also happened in this kind of system is that the threshold, how much you have to perturb your rest state to go into the excitable trajectory, is not well defined usually. But you have a region between excitation and not excitation, where you have a smaller trails around the phase space that, well, is not excitation nor the other. So nevertheless, this pseudo threshold become very narrow as eta is small. So it's better defined when we have big difference between the time scales. On the other hand, we have the type 1 excitability. That is the one that where the frequency of the oscillations goes to 0 before the excitable regime. There's two ways where we can go in these systems. We can have this bifurcation that reach to the excitable regime. First of all is the homoclinic bifurcation. Here I'm showing a sketch of this kind of systems before in the oscillatory regime. Here we can see that we have one oscillation around unstable point. And in this kind of system, we need for more phases point. So we have here a saddle point that is a point that is unstable in one direction. And the rest state that is the stable point that will be when in the excitable regime, the rest state of the system. So here we have the oscillatory regime. When we change little by little the parameter to go into the excitable regime, this cycle is going to grow, it's going to approach to the saddle point here, and there's going to be divergence of the period of this point. No? And this divergence is going to be logarithmic. We are approaching here to the limit. The frequency is going becoming very small, and well, it's the same as saying that the period is diverging. At some point, it's going to touch the saddle. We are going to have this homoclinic bifurcation where the cycle is destroyed. And on this homoclinic bifurcation, what we have is an homoclinic connection. That is this saddle. There is a trajectory that goes away from it, but come back again. No? Here I'm plotting it here. I'm plotting the time versus the one variable versus the time. And we can see how this trajectory left the saddle point, this dotted line here, and come back again. And after this bifurcation, where the cycle is destroyed, we are in the excitable regime. Here we can see that if we give an initial condition that is above this line here, that is the stable manifold of the saddle, it will make this all trip around the phase space. Here I saw it in red, and go finally to the rest point. On the other hand, if we give just a small perturbation, it will dump down, like the blue line here. There is other ways to get into type 1 excitability. For example, a SNIC, that is a saddle node invariant cycle, is similar to the other one, but well, here we have a cycle again, and at some point there's going to appear, there's going to be a saddle node bifurcation, that is a bifurcation where two different fixed points are created, and it's going to happen in that cycle. So it's going to break it. When approaching here, there is also a divergent of the period of this cycle. In this case, it's going to diverge as a power law here. So there is a difference in the divergence in both cases. And after that, the cycle is broken, and we are again having an excitable behavior. No, we have again the saddle. And if we initiate the system above that point, it will travel around and come again to the rest point. On the other hand, if we put it down, it will go down. So here I'm going to write again the difference between the two kinds of excitability to make it clear. The excitability occurs with a sudden destruction of these large amplitude cycles. In the type 1, it has zero frequency at this bifurcation, while in the type 2, it don't. This in the type 1 occur in a homoclinic or a SNIC. Here I draw the homoclinic because it's what the bifurcation I'm going to talk mostly during the talk, but also the SNIC. And on the other hand, in the type 2, it occurs in a Hopwood carnot. In type 1, we don't need this separation of timescales, while in type 2, usually the systems need of this slow fast separation. Here we have a well-defined threshold, this line here I told you before, while in type 2 we have the pseudo threshold that is not so well defined. Here I have this plot where we are in the excitable regime in the Fitzhugh-Nagumo system, and we can see how if we make a small perturbation of the system, it makes all these small trajectories, or it got damp. But if we have to cross like a what they call here no man's land, like a region where, yeah, this pseudo threshold, no. Finally, type 1, the duration of the excitable trajectory depends on the initial condition. If you put an initial condition that's very close to the threshold, it, yeah. And in the type 2, the duration is well defined. So what happened when we put space in this kind of system? Here I put this, I put different a string of balls, with each one of them have excitable local temporal excitable dynamics. And imagine that they are attached together with strings. So if we put a small perturbation to one of them and push it up, what you will expect is that this one will grow and will follow the excitable trajectory. It will push up the neighbors, and that will make that the neighbors will get excited also, and this excitation will propagate in space, making two pulses. It's propagating in a different direction. So this is similar to what happened in a Mexican wave in stadiums, that one person stand up and the neighbors will stand up, and this will be propagated in the stadium. Also, the other day I found in Twitter this other example, that is a species of bee that creates this colony that, well, they live outside the nest, and they make this kind of behavior to scare predators, like for example wasp or something. In this case, one bee is pushing the abdomen up and the neighbors are following. So it's more or less the same behavior. Nevertheless, usually in physics we use continuous mediums instead of these discrete mediums, where we are working with reaction diffusion systems. So in this system, we have a reaction part that obey the local stability dynamics I showed you before. But if we consider, well, yeah, sorry, one thing. This is following by the local part, but also can be understood as if we put an homogeneous perturbation to the system, it will follow this, no? Because the diffusion is not going to play a role there. If we consider the full system and we put localized initial condition, we'll have spatiotemporal excitability. So for example, I have here a plot where I'm putting time and space. And well, we have here one of the variables of the system, one of the fields. And we initiate the system with a localized initial condition, a Gaussian here down. And in this Gaussian is going to create two pulses moving in different, in the opposite directions. No? We can isolate one of these pulses, and well, it's a traveling pulse. No, it's a pulse that travels in space without changing its shape with a given velocity c. These pulses somehow transcribe in space what the local dynamics is doing in time. No, here you can see how these go up and then go down. These seem a little bit weird because are mirrored image one of the other, but one can interpret this as how it's going to behave one single point of the space when these traveling pulses go through it. No, so first it's going to go up, just in the local stability case. It's going to go down, and it's going to dump to the rest state. No, so yeah, there is this transcription of space, time into space. In the case of type 2 excitable media, this is well studied in the literature, and these pulses can be interpreted and relate with temporal dynamics. This is done by considering the pulses, like this one shown here, as two fronts that face each other. No? We will have one first front, this one going from D to F. Here will be this one. Then we'll have some region where we have the slow dynamics ruling. And then on the back, we have another front going from J to I that, well, is chasing the other one at the same velocity. And finally, this tail here that is also given by the slow dynamics. So these results have been applicable to many systems. For example, hair tissues. One pulse of these zones will be a normal beat of the heart, but the instability or change in this kind of pulses could be different kind of heart illness. For example, tachycardia in the case where there's pulses instability in a spiral, or when these pulses break and goes to a turbulent regime, we will have something like this that could be associated with fibrillation. It has been also used in other kinds of systems, for example, chemical reactions. Well, some kind of chemical reactions have behaviors that can be associated and explained with this. And in general, type 2 excitability has been used as a reference to describe any excitable media. Nevertheless, during the last years have appeared some excitable systems, like the one I told you before of Posidonia oceanica, where looking for the mechanisms that generate this kind of behavior cannot be associated with the ones of the type 2 excitability, but with the type 1. So for example, we have the Posidonia oceanica, with the mechanism seems to be a kind of autotoxicity. The plants were died, generates this surface that get attached in the ground. So the places where Posidonia have died is the mortality grows and no more plants can grow there. No? In the other hand, it propagates to places where there is that haven't been this death Posidonia. No? There are other examples. For example, we have this grass in highlands in Chile, where we can see similar behaviors. Here, they are associated with grazing of animals, And the model proposes are not compatible with type 2, but with type 1. We have also this example that are also grass in wetlands in China, that they explain this kind of behaviors with also without autotoxicity models, no? And they also have these rings that expand and are neither compatible with type 2. So yeah, what we wanted to do with this work is try to, in the case of type 1 excitable media, to connect what we have here, the local dynamics, the temporal excitability, with the spatiotemporal features that we have, that are these pulses. In particular, what we wanted to connect is the bifurcation that generates this local excitability with the spatiotemporal features. So to do so, what we have done is we have created a reaction diffusion model. We started from the reaction part. We take these equations here that are a normal form for a high codimension point that give a complete description of type 1 excitability. No? So with this equation, we can explain the temporal excitability pretty well. And we have add a diffusion term to it. So, well, we fixed some parameters because this one has 4, and it was a little bit complicated to work with that. And we let the mu1 and mu2 as control parameters. And studying this system, we will give a description of the temporal phases diagram. But for this talk, we are only interested in very little of all these bifurcations. That's it. That are this yellow one, that is the homoclinic bifurcation. I told you before that was one of the limits of the excitable media. And the SNIC, this one, that's dotted line, blue there, that is other of the boundary of this region. So in this case, in all this gray region here, we have excitable behavior. And what we are going to do now is to add a space, no? So what happened when we add a space to this system? We have found excitable pulses here in the green region here. Well, here, yeah. There are some bifurcation that delimitate the region of stability of these pulses. But in this talk, I'm going to focus just in this little part here to have, well, yeah, the same scale more or less between both. Anyway, for make it more easy to compare, I have plotted here also the temporal bifurcation. Here in this orange line is the limit of the temporal excitability through the homoclinic. And this blue dotted line is the SNIC, no? And we can see how in the SNIC case, it's pretty obvious that the spatiotemporal pulses exist until the very limit, no? Until the SNIC. In the case of the homoclinic, on the other hand, we have this dark with this black line there that goes really, really close to the homoclinic. It's not exactly the same point, but well, I will prove now that that two lines, the homoclinic, the temporal homoclinic, and the black line that we have called double heteroclinic bifurcation, are connected. Yeah. So to do so, what we have to do first is give a better description of the pulses. For do so, notice that the pulses is a special solution of this kind of systems because they are solutions that travel without changing its shape with a given velocity. And therefore, instead of depend on space in time, if we move with them in a mobile reference frame, we can see them as steady solutions of this system. And therefore, they can be described embedded with space and time with only one variable, c, that is linear combination of the other two. No? Here we define it as x minus the velocity times the time. So as this fields only depend on one thing, well, instead of we can impose this in our partial differential equation, and with some chains, we arrive to a system that describes this kind of solution. This solution that travels in space without changing its shape with a given velocity. No? This is what we call the moving reference frame system. And as you can see here, it depends also in the velocity, no? In the velocity of that solutions. So in this system, trajectories of this system will describe the shape of traveling solutions of the PDE that travel without changing its shape. To get one of these solutions, we have to tune the velocity to have the velocity of that structure, and then we can find it here. And well, as I told you, one of the solution of this system will describe the traveling structures, and I'm going to give some of them that I will use in the next slides. So, for example, a fixed point in the moving reference frame system that are points that do not change in space neither in time will be homogeneous steady state, no? Homogeneous state that do not change. Homoclinic connections of this moving reference frame system that are a trajectory that goes from one point and come back to itself will describe traveling pulses. Heteroclinic connections that are a trajectory that goes from one fixed point to another will describe fronts that goes from one to another. And finally, cycles, limit cycles of this moving reference frame system will describe traveling waves, no? Train of waves. So these periodic solutions that move in space without changing its shape. So now what we have so far, we have our system that is defined by a partial differential equation system. From this partial differential equation system, we have two kinds of solutions that are important for us now. On one hand, we have the homogeneous trajectories, that is how behave the system when we initiate it with well-missed initial condition. This is described by the local dynamics, that is where we have local excitability, I explained at the beginning. On the other hand, we have traveling structures, like the pulses. These ones are described by the moving reference frame system. And what we want to do now is to connect this kind of solutions here with this here, with the local excitability. Well, exactly with the bifurcation that generates the homoclinic bifurcation. As I told you before, in the moving reference system, the pulses are homoclinic connections. So, yeah, seems a little bit that this is going to be the way, to connect these two things. But there are two problems. First of all, that this homoclinic connection is a homoclinic connection of the rest state. So this point down. While this homoclinic bifurcation here, that is the one that generates the local excitability, is a bifurcation of the saddle, that is this point that is on the top. So, well, I'm going to explain how to go with that. But the second problem that we have is that we don't have a bridge between the two different systems, no? We don't know how to connect this with this. Well, luckily, there is a way to connect them that is going to the limit where the velocity is really high, where the velocity goes to infinity. I'm going to prove it now a little bit. Here we have our moving reference frame, and we can see that if we make the velocity go very big, so we are studying a structure that moves really, really fast, but the first derivative goes to 0, so it's a structure that are pretty flat but moves really fast, we can recover from there the local dynamics. Well, you can do the maths, it's not hard, but maybe to understand it's a little bit hard, so I'm going to make an analogy that is with tides. So tides, that is, well, this very, can be understand the tides as very, very, very big waves with a period of around 20,000 kilometers that moves really fast on the Earth's surface, like around 1,600 kilometers per hour. Nevertheless, when you are on the beach or on the sea or on a port, you just see everything as a homogeneous move of the water. No? So here we have this traveling wave that is very flat, move really very fast. But when you are there, you just see it approximately as a homogeneous movement of the sea. No? Obviously, tides do not work like that, but I think it's a good analogy to understand the limit I'm talking about. So, okay, now we have this connection between the moving reference frame and the local dynamics. Now we go with the second problem, that is how we make that those two homoclinic connections happen for the same point. Well, to understand that, we are going to approach this black line that is the bifurcation of the spatiotemporal dynamic, the spatiotemporal system that destroy these pulses. And what happened when we approach there is that the pulses start to develop a little tail that becomes a plateau on the saddle point. No? Here, what I'm plotting is the norm of the pulses minus the norm of the homogeneous state as a function of one control parameter mu to approach to the bifurcation, and we can see how this diverge. This diverge because of this plateau that is growing on the back of the pulse. If I go here, we have the 0.3. It's small. 0.2 it become a little bit longer. Here it become much longer. Until, well, this divergence we have studied it is logarithmic. This is similar to the divergence of the period that we saw in the homoclinic bifurcation in the local dynamics. But what happens here is that when we arrive to the bifurcation point, we cannot understand the pulse as a pulse anymore, but as two fronts touching each other with a very big plateau in the middle. No? So we have this front that moves really fast. Well, not really fast. It moves with velocity c, and it have on the back this very, 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 very large plateau, almost infinity. And at the end, we have this other front that close the pulses. No? So when we separate a little bit from the bifurcation point where these two fronts exist, we will have our pulse with the ground state. But also we can think that these two fronts could interact in a different way. No? So if we put the front the other way around, we have now a front starting from the saddle point, then a very large plateau on the rest state, and then it will come back again to the saddle point. No? And if we go a little bit away from the bifurcation point where this front exists, it appears a pulse that now is on the unstable state. So we were able to connect this pulse on the ground state with a pulse on the saddle just by going through this bifurcation. So these two solutions are part of the manifold of this point here. Here, what I'm plotting is the velocity as a function of mu that for some reason is cut here. But well, this is a control parameter. What we have in this solid line is the traveling pulse on the ground state. That is the excitable pulses that we find in our system. When they start approaching this point here, they start to develop this plateau on the back until we arrive there, and we have these two fronts facing each other. No? This description I just told. After that, it appeared this other line. Okay, this dotted line here. That is the other solution, no? The solution where we have a traveling pulse, but on the unstable state. Then we approach in the parameter, when the parameter approach this vertical line here that describes the temporal homoclinic, we can see how our pulse, this one, diverge in velocity. And as I told you before, when the velocity becomes really high, the moving reference system converts to the local dynamics. So this solution converts to the homoclinic solution of the temporal system. So now we were able, thanks to this point here, to connect the temporal excitability with the spatiotemporal traveling structures. No? And as you can see here, both bifurcations do not happen at the same time, but there is a small gap between them in the parameter space. Okay. I'm mute now, or I'm still? Okay, but I'm still, yeah, okay. Nice. Sorry. Now I'm going to give some results on this system. For example, what happened when we approach to the SNIC. In the SNIC, what we have, as I told you, here we have the excitable local excitability. Here appears this point here, and here we have the cycles, no? And we are going to approach to this region here, looking to the traveling pulses, no? We get something like this. Here I'm putting again the velocity as a function of the control parameter. We have the traveling pulses at this blue solid line, and what we have here, this purple line going up, is a saddle node of the moment reference frame that occurs for the same parameter of the saddle node of the temporal dynamics, something like that. And well, we have studied in this region what happened to the pulse there, and it seems that this can be associated with a saddle node separatrix loop bifurcation that separates a region where the saddle node of the moving reference frame is just a saddle node outside of the cycle, and from there it becomes a saddle node in the cycle, no? And well, as C goes to infinity, it converts to the bifurcation that we see in the temporal dynamics. Finally, the final result of this work will be what is happening here, no? You told us that well, you are relating the temporal excitability with spatiotemporal excitability, but here there is a small region of stable traveling pulses that is outside of the local excitable region. Well, what is happening there is that these pulses also can be associated with other kind of structures that are structures associated with these stable systems. So, okay, what I'm putting here is again a control parameter. Here I'm plotting the maximum of one of the fields. Here we have our pulses, and as we can see, this will be the excitable region. Here the pulses exist and is stable. At some point it becomes unstable, but we can still track them for different parameters, and we track them back to these structures here that are localized structures that do not change in time, so they are steady, and they seem to, in this kind of systems where there is excitable behaviors, they instabilize themselves in a Dries picture bifurcation. So these solutions are symmetric, but at some point of the parameter they have a spontaneous break of symmetry, and it appears these pulses that are the one that we are seeing far away in the excitable regime that born from here in the spontaneous break of this symmetry, and they start moving. So some conclusions, what we have seen today is, well, we use a general system with local excitability, and we add diffusion to it. We found and characterized excitable traveling pulses using the moving reference frame. This moving reference frame can be connected with the temporal dynamics through the limit when the velocity becomes really large. And in this limit, we were able to connect the bifurcation of the pulses with the bifurcation of the temporal system. And finally, outside of this region, we will connect these traveling pulses with the localized structures. So, well, yeah, this is still an open problem because it seems that there are many ways to get these traveling pulses, but we haven't still connect everything, no? So we have still some work to do there, no? Why this bistable can be in stabilized kinetic pulses, but also the suitability, how is everything connected? Finally, as a remark, I want to say that, well, we see that there is two different ways to arrive to this kind of excitable behavior, the type 1 and type 2. Nevertheless, the emergent phenomena of excitability is not very different from in one kind of system and one kind of other kind of system. So looking to the structures that appears in the system don't seem to give you a lot of information of if this system is type 1 or type 2. Here I put some different systems. This is a chemical one. These two are plants. These are one illness of the tongue that is called geographic tongue. So some of them are type 1, some of them are type 2, but at the end, if you look at the behavior of the system, it's hard to differentiate one from the other. You have to go to the mechanism, the physical mechanism behind this. So this is all. Thank you very much for your attention.
Well, very good. Pablo, thanks a lot. So, yeah, if there is any question in the audience.
Yeah, so I would like to ask, because you seem to be covering a very particular and specific, for example, when you showed the homoclinic cycles, etc. So how, in a natural system, so in the real world, your system is very likely to have change in parameters and, to maybe be subject to a lot of variability in the parameters it's characterized by. So how do you think a system can arrive and stay in that regime? I don't know if I am explaining myself clearly.
Okay. Okay. The bifurcation point where the system changes from one regime to another, it's true that it's a codimension one point. So to be just there, you have to fit the parameters, and it's impossible in natural systems, no, usually. But what this bifurcation separates is two different regimes. No? You are separating the oscillatory regime from the excitable regime, and that are larger regimes of the parameter space. No? So you can cross it and be completely in the excitable regime of the system. No, I don't know if that's the question.
Yeah, more or less.
More or less. Okay.
Thank you very much for your talk. It was really nice. I didn't quite get which is the physical difference between the systems that you explained at the beginning, that like this Poseidonia Oceanica compared to the heart, for example, that makes that you cannot model Poseidonia with type 2 excitability.
This comes from the, we saw this kind of behavior in Poseidonia, and we proposed a model. This model was that, well, we have two different fields. One is the Poseidonia fields that they reproduce clonally, whatever. And when this Poseidonia dies and decomposes, generates this substance, the sulfates that are toxic for the Poseidonia. No? So we have these two different fields, and we describe how these fields interact, well, by our microscopic point of view of how this system was working. No? Nevertheless, when seeing what are the bifurcation or what are the behavior of these systems, just looking to the local dynamics, we saw that they do not have these things needed for type 2 excitability. No? But they have these cycles that breaks in a homoclinic and generates this kind of excitability just in the region where we expected it to have these pulses. No? So this suggests to us that, well, maybe is this type 1 excitability what is doing this kind of pulses and not the type 1, the type 2. No? But again, what I told at the end, just look into the Posidonia. It's hard to know if this one or another. You have to go to the physical mechanism behind it.
Okay, thank you very much.
Your bifurcation diagrams for the case of spatiotemporal excitability has an additional parameter which is c, which is the velocity. It's a parameter which is not in original equation. So you look for particular solutions with a parameter c, and then the diagram includes this additional parameter c. In reality, when you have the initial system where there is no c, you make a perturbation. And is c unique? Is c selected in some way? What is the value of c?
Okay, well, I'm going to put as an example maybe well, this diagram could work. Yeah, all the different scenarios with different C's, all the different, okay. For each C, we have one configuration for the moving reference frame system, but all the solutions of this system coexist with different C's in the partial differential equation system. The thing is that some of those will be stable, some of those will be unstable, and at the end, when you have one of these structures that is stable, for example, the pulses in the stability region, the system will converge to that kind of solutions. No? For example, this one here. Here you can see that this line where that describes the traveling pulses is codimension 1. No? You have to fix the velocity at the parameter point to land on that place. But in the partial differential equation system, it just go there because of that solution is stable. No?
Oh, yeah, but, well, this was my question. Have you studied when is this stable? For example, for fronts into unstable states, homogeneous fronts onto unstable states, there are many cases in which there is you can derive which is this velocity, it's a marginal velocity that you can calculate. I don't know if there is something similar here, that you have, there is one C that is the one which is stable and all the others are not. Is this the case or is not studied at all?
In the case of traveling pulses, they only have one velocity. There is not a different traveling pulses with different velocities. There is only one velocity that have traveling pulses. I don't know if that's the question. Sorry, I'm.
Yeah, traveling pulses here are dimension
one.
What fronts are dimension?
Yeah, usually if you have solitons, the solitons are dependent of the initial conditions. No, you have initial conditions that could give you different solitons that propagate with different velocities. Here, there is only one traveling pulses for any parameter of the partial differential equation, and that. Yeah. And on the other hand, there is also, for example, with wave trains, is all this region here. So yeah, you can characterize this by the velocity. But with traveling pulses, there is only one.
Any more questions?
No, it may be a very easy one, but if you go to the super diagram of the super bifurcations, why are you adding the diffusion term? Or maybe that's the key. Why is the diffusion term for?
Well, the diffusion term, well, we have a reaction diffusion model, no? So you have if you just have the reaction part, that system will not be space extended, no?
Okay, it's only temporal.
It will be only temporal. Adding the diffusion term, we make this system, well, that we can have solutions that depend on space. No?
Okay, nice. That's what I thought. But also then later, this cuspid that you have may have a, I don't know if I have understood it wrong, but if you just have the temporal domain, there is a hop that is explaining that this kind of thing that then, well, you have this loophole and then it's growing and then you have the saddle and the kind of thing that you were explaining. the diagram. And if you have the spatiotemporal, you have the SNC, or both kind of bifurcations, the hop and the SNC are happening in the cusp for the temporal and the spatiotemporal.
With cusp you're talking about, sorry?
This kind of triangle that you have there, and also you have there on the the temporal thing.
Okay, the local dynamics and the spatiotemporal dynamics are connected in this limit when t goes to infinity. So the bifurcation that you have on the local dynamics also goes down in the spatiotemporal dynamics. For example, the saddle nodes that generate the pulses as well in the space extended system, they will describe the creation of homogeneous solutions. And these homogeneous solutions are not dependent on the velocity. No? You can move an homogeneous solution at the velocity you want, and it's going to still be a solution. No? So in this case, the saddle nodes, they are for the same parameters that in both systems.
Okay.
I don't know. I'm not understanding you very well, but I think.
No, I was okay. So the kind of bifurcations that appear are the same in the temporal and the spatiotemporal. That's maybe a better question.
Some of them yes, some of them no.
Okay.
For example, the double heteroclinic connection cannot exist in just a temporal regime because it needs for more dimensions.
Okay. Okay.
There are more in the spatial. Okay. I don't know if there are any question in the people looking to the seminar remotely. If so, just unmute yourself and just let. Yeah. Seems like it's not. So we'll stop here the session. Let's thank Pablo again for the program. Thank you all for coming.
Bien, ¿te ha gustado? Ya.